So yeah, we're basically we're just going to go through some of the key components of Firebolt and how they particularly apply in the ad tech space. So a bit of background about me first. So I'm Matthew Darwin, a solution architect here with Firebolt. I've been with the company for just over a year now. My background was as a DBA for a long time, and then worked as a consultant on various cloud data platforms, all three sort of major cloud vendors, and touching a lot of different technologies in there. And what we have seen over the past 10, 15 years is volumes of data increasing massively, and a lot of focus on the ability of storing that data sets, but not necessarily on querying them effectively. So we're going to just kind of go through what we'll be looking at here. So yeah, more data equals more problems. The larger the data set that you have a lot more things to consider, such as cost control, how you actually store that data. If you're looking at storing this on premise, for example, you would have to have the ability to scale your internal systems easily, frequently, which is not really viable. And then querying it as well becomes more problematic, especially when you're aggregating over huge sets of data. So we're then going to look at some of our Firebolt demos, some of the queries that we have using a real use case that one of our customers brought to us. So the data itself is slightly obfuscated, but it is a real data set that they have. So we'll go through that. And then we're going to look at a couple of different kind of things that Firebolt brings to the equation that would help with those kind of queries. Lastly, we've got a little bit of an approach to handling Clickstream data with SQL, where you need to have infer relationships between those tables. It's the typical fact-to-fact join, which are always going to be slow on a lot of systems. And then we'll break out into some rooms and have some of those discussions. So terabyte is the new gigabyte in data, and I'm sure you're all in that kind of scale now. If you haven't got gigabytes yet, maybe it's because you're as part of the startup and you're just kind of warming up, but I'm sure you have that in mind that you're going to be hitting terabytes and terabytes of data, and quickly as well. We frequently talk to customers who say we have 3, 4, 5 terabytes of data being generated per day, and how do we manage that over time? We have a rise in what we'd like to call a data wrap. So if we think of traditional BI, you would be looking at analytics internally in an organization. A report taking 30, 40 seconds or 2 or 3 minutes is not necessarily considered a problem in a lot of organizations. But as soon as you start to expose that to your customers, that perception and expectation changes. People no longer want to wait 30, 40 seconds in an app on a mobile phone, etc. We're expecting sub-second consumer grade experiences there. And that's those are the kind of things that we like to call data apps. And then what we've seen over the last number of years in the analytics space is that compromise comes into place. So we have to put limitations on what we're doing in order to achieve it. So when we're aggregating data, we'll put that into our pipeline. So we'll pre-aggregate data to allow those reports to be speedy. But that means that we can no longer have granularity. We can't drill into those reports easily. We can't drill into that data easily and understand what was creating it. And we lose freshness. If you're aggregating data as part of a data pipeline, that has latency involved in it. And typically people will be running these maybe daily, maybe, so I'm just having a look in the chat window as well there. So the, maybe the data is aggregated daily or, every hour or so on and so forth. So you lose that ability to be dynamic with your data. The other thing that happens is we reduce the time windows that we're preparing this over. So you lose some of the depth of what you're looking at. It becomes impossible to store the amount of data that you have over those huge periods, or even if you're aggregating into summary tables, you can't do that across your entire 5, 6 years worth of data collection. You have to trim it down to, say, the last month or the last quarter, or you're only going to go to granularity of, say, a year if you're going back more than 1 or 2 years. The third choice is we accept those slow dashboards and frustrated users, going back into the more traditional approach. Now, in some cases, we've seen reports that take days to run. That's really not something that you can rely on. Or then we kind of have to glue lots of different solutions together into really complex engineering projects. And I'm sure we're all familiar with the modern data stack. I'm sure we're all familiar with the number of different vendors and icons that get put onto those kind of architecture diagrams to solve these problems, where a separate tool is being used for each little niche of data that's being exposed. Now, that's great in a lot of ways, use the right tool for the right job, but it adds cost and it adds complexity. And the cost is not just in the tools themselves, the cost is also in the engineering that needs to go into integrating those engineering projects together. So I'm just going to show you a very quick demo now. Okay, so what we like to start the demo with is an actual dashboard. So this is a superset dashboard from one of our customers. They actually use Looker, but I prefer doing the demo on superset because it's slightly quicker as actually a dashboarding tool. And the volume of data here is a 54 billion row table. It's around about 31 terabytes. 31 terabytes of data. And the dashboard is the usual kind of thing. We're going to drill into impressions, click-through rate, clicks, and so on, to get an idea of what's happening with those particular apps and media sources. Now, with the use case originally, this dashboard here, which is, if I show you the filter, is across a 1 week period, was taking up to 45 to 50 seconds to load. Frequent timeouts in there. Some of these windows would be just circling and timing out. It's quite a frustrating experience. So it's definitely one where you would go and load up your dashboard, go and make a cup of coffee, come back, and hopefully it's loaded. And for something that would then be exposed to customers, that's just not an acceptable experience. So I'm just going to go ahead and start tweaking some of the filters while I'm talking, so you can see the difference in performance now with this dashboard. Now, bear in mind that each one of these changes is physically going and running those queries against Firebolt in the background. So behind each panel here, there is a separate query that's being run against Firebolt and returning that data in real time. So it's not, we don't have cached results going on here. Firebolt itself doesn't cache results. Each of those queries will be being run. So if the data was against a live instance with data flowing in, the numbers would change as we go through it. So I'm going to increase again up to a larger window. And these are the kind of windows that the customer simply wasn't able to run on their original system. They would just time out. Whereas you can see here, we've got now something that is a relatively snappy experience. I can dive in, chop and change what I'm looking at, get the results back quickly. I'm going to pop in, let's go for a smaller date range. Let's tweak out the media source. And so you can see the experience from a user perspective that belies the fact that this is running against 31 terabytes of data and sort of 54 billion rows. So if we delve into how we actually do that within Firebolt, I'm going to show you the Firebolt UI here, which is kind of a bit funny on this. Okay, so the table that we're looking at is a table called LTV. Can you see that okay? Do you need the screen a little bit bigger, everybody?
Oh, it's okay.
Cool.
It's okay.
So you can see, we've got, 57 billion rows, not 54 billion rows. And if we look at the table itself, it's this LTV table here. We have a primary index on that, which I'll talk about in a moment. We have the 31 terabytes of data uncompressed. So the data, if you actually wrote this data out just as text files and CSV or whatever, that's the kind of size that we'd be looking at. Within Firebolt, that compresses down to about 1.8 terabytes. So you can see the first efficiency gain that we're going to have. We're going to have there in Firebolt. The other thing that we have is we have some indexing in place. So we have a primary index, which you can see is sorted by the timestamp date, the media source, and the app ID. So that's going to allow us to do good pruning of the data. And then the second thing that we have is what we call an aggregating index. And I'm going to talk about those in further detail in a minute. But you'll see that that takes us down to a size of table that's 20 gigs. So really, when we're querying this data now, we've gone from having, 30 odd terabytes down to 20 gigabytes, which is actually a manageable amount of data to work with. So if we go to the query itself, this query here is the query that powers this section of the dashboard at the bottom. So it's the most granular portion of that data. And I'm just going to run that for you now on our analytics engine here and get the actual runtime from that. So you can see that we're about 0.4 seconds for this query. But the really crucial thing that I want to kind of pay attention to here from an ad tech perspective is the amount of data that's being scanned. So we're now down to 3.2 gig of data as opposed to 30 terabytes of data. And this is where the efficiency is coming from to allow us to do these analytical queries fast. There's no magic here. We're not somehow processing all of that 30 terabytes in 0.4 seconds. No, we're trying to intelligently work with the data that we have in order to deliver it quickly. And as I increase up the window of time here, you'll see that starts to change and affect the query time. So if we do 2 weeks, it's 0.47 seconds. We're up to 5 gig. As I increase it further to a full month, you'll see that we then have 10.42 gig of data being scanned there for that full month. And from the point of view of the customer, we're also now able to do something that simply couldn't do before, which is run this across all of their media sources. We have a query now that runs in just over a second, scanning about 11 gigabytes of data. And previously, this would just not work on where they were at. So I'm just going to pause for breath there for a second. Just start thinking about how you might apply this in your own environment. Are there issues that come from just the volume of data that these solutions will kind of work with what you have? So the key part of how we're gaining some of that, I talked about aggregating indexes a moment ago. An aggregating index is something that we have in place that will allow you to simplify your data pipelines. So as with any index, it's a declare once operation. So when I create my table, I'll create this aggregating index alongside it, and that will then be maintained automatically as you insert data into the table. And if we look at the composition of it, it looks very, very similar to the query that we're running. So you can see that we have various aggregations here across the different metrics that we have. We've got a couple of counts. We've got a couple of sort of filtered aggregations where we're looking for installs. And then we have the columns that we're going to be filtering by. And it's important to note that the aggregating index also has its own internal index. So these columns are going to affect the sorting of this table. So if I'm filtering by timestamp date, I'm always going to get good response rates out of this particular query. And if we look back at the query that we have, you should start to see that these aggregations all look very familiar. There's nothing here that doesn't exist within that aggregating index. And so if I run our explain plan over the top of it, you'll get to see we're actually using our aggregating index here as the primary index. And the primary index of that is being used rather than the base table itself. But when I look at the query that I have, all I'm querying is the LTV table. I don't have to go and rewrite my queries to point at the aggregating index directly. Firebolt will do that for you at optimization stage. So if a query can be covered by an aggregating index, it will go about and use that aggregating index for you. You don't have to worry about it. And I think this is where, the simplification of data pipelines really. Okay, so what we're looking at here is for the builders of next-gen ad tech experiences, we're now able to deliver that sub-second analytics experiences at terabyte scale, but while keeping the hardware resources low and without painful trade-offs. So the advantages that we have of reducing that data sizes down into the gigabyte level instead of the terabyte level means that you can run this on smaller hardware. So my 20 gigabyte aggregating index that I had previously, I can load that in full to the cache of compute instance and not need to be churning data having spills or anything like that. I can have that literally loaded, ready for querying at every opportunity. We have a modern cloud native architecture. So we have storage and compute decoupled, as you would expect. So long-term storage of Firebolt data is in AWS S3, but then that data is also loaded into the engine directly onto its SSD. So you have decoupling of multiple different engines that are capable of spinning up that will not clash with each other from a workload perspective. And this has the added advantage that you can start to tune those specifically to their workload. So if we look at an ingest workload where you might need more memory intensive operations, you can put that onto specific compute resource for it. Whereas if you have more compute-based queries that are running that are performing calculations, you can run those on a more compute-intensive hardware. And then, we have it built for developers and data engineers. So we have the ability to slot this into your data stack so that you can deliver data apps quickly and reliably. We have good support everything's within SQL. So that's how you would primarily interact with Firebolt. We have SDKs and Node, Python, and a good API in order to interact with that, so that you can start to really deliver what you need from data apps. Now, typically we see people using data apps with a custom built application. But if you are then using something like Superset or Tableau or Looker, we also have the connectors for those. And we have connectors for things like Airflow and so on. So you can plug it into your existing data stack. And then the reason that we have our performance optimizations in place is because we've designed this in order to scan less data from the ground up. So whilst we've got that huge amount of data there, we're looking at having individual queries that are looking for very small and specific parts of that and try to optimize how we read as little data as possible. So we have all of our tables with sparse indexing. So the data itself will be sorted, and then we have the sparse index over the top of it that points to those date ranges within that file. So when you run a Firebolt query, it will be loading as little of those date ranges as possible in order to allow you to query it as effectively as possible. And it frees us from doing those big table scans. You're actually targeting the data much more smallly and loading that from there. And we have done that through a proprietary file format called FFF. And as we say, that data is then sorted and compressed, stored on S3 for you, and loaded into your engines when you query that data. Primary indexes aren't particularly complex to understand, and if you've worked with any database engine that uses any form of clustering index, it's exactly the same thing. So MySQL, SQL Server, it's the same thought process that goes into that. You would have your first column will sort the data, the second column will sub-sort the data from that, and so on through the columns that you have. But what they're also used for is compression as well. So a well-defined primary index within Firebolt will get you really good compression ratios and really help with the speed as you're going forwards. And we then have two further types of index. We have the aggregating index, which I showed you in the demo. And they are great for repeated workloads such as dashboards and reports and known workloads that you have, like the data apps that we typically talk about. They can be then used on much smaller cluster sizes. So I can have my ingest run on a large cluster that needs to do the work to ingest that data. But then because my aggregating indexes are really a thin slice of that, you can have those running on much smaller hardware, which makes it much more cost effective for your applications. The second type of index that we have is a join index. So this is effectively works as a lookup to allow you to denormalize your schemas as you would do. You don't have to store all of your labels in there and worry about how you handle that inside your large fact tables. You can store those separately as you would do in a normal dimension table. Those join indexes are stored in RAM and will be used as a lookup when you actually perform the query. So they can be used against both base table and aggregating indexes, sorry. And they can really speed up that performance when you're getting to returning the label kind of data that you would want. In terms of the architecture, those of you who are familiar with Snowflake will see something very similar here. It's a very similar architecture overall. So you would have your data in externally, however you want to do that as part of your pipeline, exported from the data sources that you want, land that into S3, and then we will ingest that into Firebolt. The long-term storage for Firebolt is in AWS 3. And then that is then delivered to each engine as you would be querying it. So if you see here, we have an ingest engine that will be doing the ingest, and that will write the data out into the Firebolt S3 backend for you. We then might have different use cases. So we might have a reporting engine. We might have an ad hoc query engine. We might have a custom app engine. And each of those will run on its own resources, scaled in the way that they need to be scaled to deliver their use case. So you can start to really separate these out for what you need to run your data. And then we have a lot of engine options in here. So we have 4 main types: compute optimized, SSD optimized, RAM optimized, and then balanced, which is kind of a mixture of the other 3. But what this means is when you come to needing to scale an engine for a particular reason, say if I have particularly RAM intensive queries and I'm doing, say, a lot of windowed functions or something like that, where the results set is loaded into RAM and then processed. Rather than having to double up my infrastructure, I can switch to a memory optimized engine in the same pricing tier, and that will double or quadruple my RAM depending on which kind of engine that you're going from. But it doesn't double and quadruple in price. So you have the flexibility to choose the engine type that you have. Same for SSDs. If you have a particularly large data set that you need to support for ad hoc querying over a long range of time. So if we're thinking you want to hold 2, 3, 4 years worth of data in your Firebolt engine, but you don't need the compute intensity that might typically go alongside that, you can go for an SSD optimized engine that will allow you to store that data comfortably in your engine for querying without having to increase the costs because you're putting suddenly 96 vCPUs in there and so on. So from an ad tech perspective, what Firebolt allows you to do is deliver efficient queries on minimally sized hardware for your workload. So it's not that we're cheap or cheaper than anybody else. It's our efficiency allows you to choose the sizing of compute that meets your workload. We have very simple and transparent pricing. We pay by the price per hour, but if you have it running for 30 minutes, you pay for 30 minutes. If you have it running for 1 minute, you pay for 1 minute. And then storage is charged at the S3 list price, which is a $23 per terabyte per month price. So it's very small scale in terms of what the cost footprint is within Firebolt. And so you don't have to worry about how much data you're storing and having particularly preventative charges there. And then it's pay as you go. So there's no upfront commitments with Firebolt. You pay for engines when you're running and you don't pay when they're stopped. Now, if you get to a point where you want to look at securing Firebolt resource, we can do commit contracts from there with some discounting, but you don't have to do that. And there's absolutely there's no imperative to do that. You can just run it as a cost, as the pay-as-you-go cost if you wish to. So the example we were showing you in the demo is this use case here from our customer apps flyer. So it's a mobile marketing attribution and analytics used internally by over 1,000 Looker users. And so they weren't able to deliver that fast experience over a full 200 terabyte data set. They replaced that custom solution with Firebolt, and now they've got to the point where they can deliver that using Firebolt and onboarding that data for them. So it also reduced their system costs massively. 5 times lower total system cost was fantastic. Oh, sorry. And then we have SimilarWeb, who are using, sorry, I mixed the slides up then. Apologies. they're again unable to deliver that fast experience over 200 terabytes data set and replace that custom solution with Firebolt. So the last thing that we want to show you, and I'm just going to stop sharing, is an example of using Clickstream data. Now, something that we see very commonly within the use cases that we're looking at are fact-to-fact joins, where we'll be looking for, say, conversion rates or something similar to that. Now, this is kind of a rudimentary example of how that might look. But we have here a table here that's called a Clickstream table with, the usual kind of event type, session ID, event time, viewer, and so on. And if we were querying that in order to look at the conversion rate between different types of events, we might have something that looks like this. So a subquery selecting our clicks where the event type is 2, going through to a conversion of an event type of 3, and we want to see how many people weren't running that. And you would typically have a query that might look like this, where we're selecting from conversions and then joining that table back to see where we have nothing matched from our clicks table. So if I run this for you now, you'll see that this is going to be quite a slow query. It's difficult to perform those granular based joins. We're at a row level here. We're not doing any kind of aggregation over the top of this. It's difficult to do those comparisons without actually performing that join on the fly due to the granular nature of the data. So you'll see here that took around about 23 seconds for the query to run. What we do support within Firebolt is a nested type. So with a little bit more creative thinking around how we model our data, we can start to get some considerable gains with this. The other thing that we can do with Firebolt is we can leverage the aggregating index that we have to then materialize this under the hood, so that as we ingest data into Firebolt, that aggregating index will be automatically updated. So I'm just going to show you what the aggregating index looks like here for this particular query. So you'll see that we have the channel ID, the session ID, and the viewer ID, the min event time, so it's the start effectively of our event, nesting the event types up within there into an array, and then counting from there. So we can see what we've got here in terms of our data as we're going to query it. So this is, again, a query just over the base table. We're not changing how we query things within Firebolt, but we're going to use this subquery with the nest in order to find those examples where the event type 3 exists, but it doesn't contain the event type 2. And you'll see a dramatic difference in the query runtime here. So from 28 seconds, we're now down to around about 5 seconds for that, just by changing how we think about the data model itself. Now, typically, if you were doing this in a more traditional data pipeline, you would have a summary table being built to do that. You would be still needing to do a lot of complexity in your data pipeline to build this kind of query. In this case, this will all happen at ingestion using the aggregating index that we have.